Passion Project Committee is committed to finding people that are passionate about fun, interesting things around campus. This could be staff, faculty, admin, and we have one presenter per quarter. And so we've chosen and worked with Mr. Salah Abed for this quarter. So thank you for joining us and for folding cranes. And please keep folding cranes while I'm talking at least. Pay attention while he's talking. So keep doing what you're doing. I'm just going to ramble up here for a little bit. You guys are good. Okay. So, Salah was working here when I first started, so I've known him for the entire time that I've been at Big Bend, which is since 2013. There's a custom in Japan called kintsugi, where broken objects are repaired with gold. And it's this lovely practice of making something broken into something beautiful. I don't know if you've seen this before with ceramics. And broken ceramics, then they repair with gold. There are a myriad of positive things I could say about my colleague and my friend, Salah. But at the top of the list, apart from the fact that he excels at using $5 words when a 50-cent one would work just fine, is that he is the master of seeing beauty and potential in that which is broken. Salah has studied language, math, music, art, and many other disciplines. His thirst for knowledge and his synthesis of his passions is why we're here tonight. So I'd like to welcome Salah to the stage, and please help me.
What Lindsay here said was technically slightly inaccurate. She was not up here in the capacity as one of the committee members. She was up here because she's one of my best friends, and I really wanted her to be the one to introduce me. So, thank you again, Lindsay. I am so honored that you're all here and that you're all here to see me. I don't know what to say. It's extremely humbling, and I really can't thank you enough. So, that was not the greeting I expected. I was going to just walk up and say, "What up, nerds?" But we do what we can here. So yeah, there's kind of a bit of a backstory here, and I suppose it does have to do with the syncresis of my interests. So I was... You're welcome. That wasn't on purpose, but you're welcome. Oh, I should unmute. There we go. Now we're cooking with fire. So I first started learning Japanese when I was 14. My high school happened to offer it. And I was a bit of a, this is probably going to come as a huge shock, but I was a bit of a nerd when I was in school. I know, I'm shocked too. And I played a lot of SNES games, Super Nintendo Entertainment System, ask your parents. And I remember that I had a subscription to Nintendo Power, ask your parents about that too. And they had a column that was something like games you'll never play. And there were these Japan exclusive games that all looked so cool. And I was like, oh man, I want to play those someday. So I took Japanese, and that didn't help at all. And I ended up minoring in Japanese, also didn't help at all. But then I got a little older and realized there was really nothing stopping me, and that during the pandemic, of course, we all were kind of a little bit time richer, maybe cash poor too. And so I just thought to myself, hey, why don't I just explore what I can do with the knowledge that I have? And from there, I decided I would take a look at math for the same reason. Now, before we get too deep into this, though, I do want to qualify something, and that is, I do not claim to be fluent. I am not a native speaker. I have spent a long time learning the language on and off again, but I do not claim that I am king Japanese learner here. So I could be wrong. I might have mistakes here. I can't promise you that everything I do is completely accurate. I've certainly done my best, but there might be mistakes. And I mentioned in the description of this talk that I really got back into Japanese right before the pandemic when my student tutor, Toshio Taki, who some of you might remember, he was one of those people who can be kind of mean sometimes, but is fun in the way that he's mean. And I'll never forget that at the end of the school year, he gave me this card, which I still have, and it basically said, in a very polite way, of course, in Japanese, that if I kept studying and kept working at it, someday I wouldn't suck. And I'll never forget how he ended it. Shiri mo tsuboreba yamato naru. Even dust piles up to make a mountain. And I remember just looking at that and smirking and thinking, you little person who's encouraging me and spurring me on. So yeah, I do still study Japanese every day. I do still try to do immersion practice, vocabulary practice, kanji practice. Now, I can't promise that everything I do here is technically accurate, but before we really get into this, I wanted to talk a bit about what math means to me, because I know that my students, which is many of you, I would imagine, I don't actually know for sure, but I would imagine that many of my students find it mystifying that I like math, because that seems like a weird thing to like. Well, really, when I first majored in math, I went to Western Washington University, which is up in Bellingham. Gorgeous campus. I really enjoyed my time there. I learned a lot. Up until that point, I thought what I imagine a lot of you think, which is that the point of a math class is to just do whatever the teacher says. And I figured, hey, I'm pretty good at obeying people. I'll just obey my way to a degree. And then I went to my third-year classes and got the biggest slice of humble pie of my life. But, and I almost washed out even. I took linear algebra from Millie Johnson, who is the best teacher I've ever had, so none of this is on her, but in fact she was wonderful and really helped me see that I had a lot more potential than I thought I did. And I hope I can do that for my students, because I know that a lot of times students can struggle against their own negative self-talk. I have students who say to me all the time, oh, I'm bad at math, or I'm not naturally suited to it. Believe it or not, I don't think I'm naturally suited to math. I don't think I have a genetic gift for it. I just didn't, or I knew that I sucked at it, but I just didn't let that stop me. I was like, oh, I suck at this thing, well, I'll just keep doing it anyway. And really how I evolved, I wanted to tell you how I see mathematics now. I see math now, you can't really tell from this, but this is the greatest game of all time, The Legend of Zelda: A Link to the Past. This game was the most important historical event of 1991. I'm sure our Russian and Ukrainian students would agree with that. And, welcome. And anyway, what I love about math is that it reminds me of a Metroidvania game or a Zelda game. At the very beginning of the game, when you first start, this is all you can access. The entire world for you is Link's house and the side of a castle. And all you have to your name is a little green jerkin, a little green piece of armor. And as the game progresses, well, math is a lot like this. And most of the classes that I took, on the first day, I didn't really know all that much. Maybe I knew a theorem or two, maybe there were some postulates or axioms that I had to take at face value. But it always turned out I could do a lot more with them than I thought I could. And so the game would progress a bit. Not long in, you get a sword and a shield from your uncle. He dies, spoiler. And then you become able to access more of the game. And then you get more items. You get a lamp, a boomerang, you get some bottles, you get all of these things. And the game will give you more and more things. And as you prove theorems, proving theorems is a lot like gathering items, because as you gather these items, you become able to solve more problems, bigger problems. You begin to see connections between things. You begin to solve puzzles you didn't know you could solve, things you didn't know you were ready for. And the scope of the world starts to expand. You can see here that the areas Link can go to get bigger and bigger and bigger. As the game progresses, he gets more items. These items allow him to get more items still. He becomes able to explore more and more of the world. And by the end, he's able to go anywhere, beat any boss, and he has just about anything that could solve any conceivable problem. Now, shields come and go, and all of these things, but at the end of it, basically, he's able to do just about anything. And really, what I always hope I want to do, or what I always want to do as a teacher, is get my students to a state where they feel like they can solve any problem. Not even just math problems, but any problem in their own lives. Because all of us have problems. Yours are obviously easier than mine, but all of us have problems. And, but the thing is, problem solving is really just about not being afraid of those problems. Because at the end of the day, you can solve a lot of problems by just asking yourself, okay, what do I know? What do I don't? Or what do I don't? What do I not know? What can I control? What can I not control? And how can I link those together? How can I make a bridge from the one to the other? And so I became passionate about these sorts of problems and because they really forced me to ask myself that. I wasn't just doing a formula out of a book and just plugging in numbers over and over and over again. Believe it or not, I find that as boring as you do. I actually get really bored if all I'm doing is plugging numbers into a formula. The way that I see math is a bit more reactive. To me, it is more like a puzzle and Zelda game. I'm like, okay, this monster's coming at me, and he's kind of scary, and I don't know what to do, but I have all these tools at my disposal. I'll just throw one at him and hope it shuts him up. And that's kind of what math is at the end of the day. It's really just sort of using all these tools in your arsenal, sometimes using them together or making bigger tools out of them, But as you do that, you become able to solve bigger problems, able to take on more things, and you'll actually find that you become a lot less afraid of your own problems in your life, even the ones that aren't necessarily made out of numbers and variables. Now then, to tie this back into Japan, there is a bit of history here. I do have to give you a brief history lesson. So for about a little over 200 years, Japan was totally isolated from the rest of the world. They would only do business with Chinese and Dutch traders, and even then, they restricted those traders to an island called Dejima, which is sort of a little trapezoidal island that just was the size of a neighborhood. And so besides that, nobody could come in. Japanese people couldn't leave or they would get put to death. And again, the only exception was this artificial island that was a port of Nagasaki, which was about the size of a soccer field. But during that time, Japanese people didn't stop doing math. It actually developed a somewhat parallel track with the math that Europe was doing. In fact, there was a method that developed in Japan that was roughly analogous even to calculus, but involved subdividing circles. And there was a famous textbook called Jinkoki by Mitsuyoshi Yoshida. It was first published in 1627. It was revised a bunch of times, and this book was extremely popular in Japan. In fact, it was said at one point that there was no household that didn't have a copy of Jinkoki. And a monk gave it that name, which means, if you break it down, truth that will not change for eternity, which to me sounds like math. That's what I like about math, is that nobody can tell me I'm wrong. I'm kidding, actually. My students tell me I'm wrong every day. But that's also part of what learning looks like. The thing is, you really do have to just be not afraid to be bad at something. The advice I give my students all the time, they think I'm joking, and I'm absolutely not joking about this. The real secret to learning any skill is give yourself permission to suck. You really just gotta be okay with having trouble with it, and just accept that as part of the process. If you can't draw anyway. If you can't sing anyway. If you can't play a musical instrument, I've been in bands. There are a lot of people who can't play instruments, but just play anyway. Well, what was interesting about this Sakoku period, this period of isolationism, is that a lot of math was done on plaques, wooden plaques, and it became common to put them on wooden tablets. These tablets were called emma, which means picture horse. And as early as the 8th century, people were dedicating pictures of horses to a shrine. Ideally, they would want to dedicate a horse to a shrine, but not everybody can afford a horse, right? I know that sounds weird to all of you in Grant County, but outside of here, there are these things called cities, and there are people who live in them who can't afford horses because they don't have space where they live. They have these things called apartments they live in, surrounded by trees and mountains. You wouldn't believe me if I told you. So, a lot of offerings didn't have horses, of course. They draw a picture of a horse, because, I mean, a picture of a horse is still pretty good, right? And what was interesting about this is that this custom evolved into doing math on these things. So the problems that involved math were called sangaku, calculation plaques. And by plaque, I don't mean like the teeth kind, I mean like the dedication kind, the thing you give to an employee for years of loyal service. And actually, during this period, mathematics was a common hobby, even among regular people. Regular farmers, samurai, regular average Joes were doing these complicated math problems. This background here is an actual picture of a sangaku plaque. And you can see here that there's a lot involving circles touching each other, touching squares, and looking for lengths of some figures when you know the lengths of other figures. So a lot of geometry going on here. And it's easy to forget, but geometry, the Greek root of geometry is measuring land or doing mathematics on land so that you can fairly apportion land. And so geometry does have a lot of applications, and what I've really been enjoying about the problems I've been doing is that there's sort of a coagination of geometry and math, which is a little bit more interesting because it feels kind of, in a way, more like being a detective. I'm figuring out what I know and what I know because of what I know. And that takes you a lot further than you might think. So about 800 of these plaques survive to this day. Back in the 1800s, a famous author actually went up and down Japan and just tried to gather every single surviving one. And he made a list of 324 of those. Some of those don't even survive anymore. And they're gorgeous. And in fact, I will show you sort of a reconstruction of one as my first thing here. So let's take a look at that. I prepared that here. So here is my first thing I put in Desmos. And this isn't an authentic plaque. This is sort of a replica, but let's see if I can read it. 直径8センチの楕円の正三角形との間に内接する赤円の直径を求めよう. So, yeah, it's obvious what that says, right?
Yeah.
I don't need to go over that. So that's the original image. And what it's saying is, effectively, the big circle has a diameter of 8 centimeters. If the big circle has a diameter of 8 centimeters, and this blue triangle is an equilateral triangle, then how big are the red circles? Which is kind of tricky. That's actually well within your power to do. It's a little bit slippery, but you can totally do it. And so I decided to do this for myself, and I did that by constructing the circle. So let's figure out what we know. First off, we know the big circle has a diameter of 8 centimeters. Okay, and what is an equilateral triangle again? What does that word mean, equilateral?
Equal sides.
Equal sides, yes indeed. They all have the same side. Okay, so the first thing I did is I drew the circle. You can't really see it here, but I did draw a circle. I called it center O, and I made the triangle inside. Okay, now you might be wondering how the heck I made that triangle. Well, if you think about it, if this whole circle has a radius of 8, you already know the distance from O to C. What would the distance from O to C have to be?
4.
Why did you all just say 4?
They used to say the radius was 8.
Diameter is 8, so the radius would be?
4.
There you go. Yeah, indeed. Okay, so that's something we can use to our advantage, and I've already started that. There we go. And so we know that length's got to be 4. Well, if I have that go all the way around, well, it ends up being the case that if I go right here, due to some tricky stuff, it turns out this length is 2, and that length is 2. So if I draw a circle right there, what's the diameter of the circle? It's going to be right there. There you go, you just did the problem. Alright, so if you feel like going to Japan, you can offer this to a temple if you want to. It's your life, I won't tell you what to do. But yes, indeed, that's what it is. And these are the kinds of problems that regular people in Japan were doing. And you can see this one isn't that hard. All of you were able to do it. And none of us did any weird fancy schmancy calculus stuff. All we did is we thought about what we knew and what we didn't know, and how we connect the one to the other. That's it. Alright, so back to my slideshow, of course. And, oh, my goodness. Okay, what have I done?
You're good.
There we go. Alright, onward. So, the isolation period ended with the Meiji Restoration in 1868. Don't worry, this is the end of my history lesson. And the pendulum swung the other way. Where Japan once didn't want any foreign influence, then they based their education system on the Western model, which survives to this day. Japanese education is still based on the Western model, although things do still work slightly differently. For instance, one big difference between Japan and America that I think can be a source of culture shock is that in America, there's always kind of that danger in American college or American high school that you might wash out. In fact, I can tell you right now, which of you, no, I'm just kidding. But there's always that little bit of danger. Well, in Japan, to get into a high school or college, you often have to take an entrance exam, which is where I'm harvesting these problems from. And these entrance exams can be ridiculously hard. I mean, they're even hard for me, and I think I'm smarter than everybody. And so they can be ridiculously difficult. But what's interesting is that the way the system works, high school and college, once you're actually in there, there's no real teeth to basically flunking an exam or not doing well. In fact, as long as you don't do anything just really stupid, graduation is de facto guaranteed. So you end up having to do a lot of work to get into the college, but once you get into the college, I'm not saying it's entirely a free ride, but it's not that difficult. You're not really fighting for your academic life like you might be in America, which is a pretty big difference. And so the current system, the math that was done back at the time was called Wasan, which just means math in Japan. And today it's called Yosan, which means Pacific Ocean math or Western style math. But I do think that, or my suspicion is that a lot of things carried over, and I want to kind of talk about those through lines that I've observed from I've done several hundred of these problems now, and I've kind of noticed some patterns, and I just wanted to go over that. First off, as you might have noticed from that previous problem, a lot of problems involve circles, and when they touch each other, when they're tangent to each other. Almost like when bubbles strike each other and they kind of nest, and you kind of figure out, okay, well, how big is this one if I know that one, and so on and so forth. So I'll show you a quick example. This is a problem from a Japanese plaque, one of those plaques that got dedicated to a shrine. I believe this one survives somewhere. And it basically says we have two circles like this, and it says that the radius of the left-hand one is R1, the radius of the right-hand one is R2, and, oh, dang it, overshot. And so the task here is to prove that the distance between them is 4R1, R2. So this is kind of a tricky one. Again, what I like about this is that this is sort of the apotheosis of analytic geometry. Those of you who are taking math classes probably hear analytic geometry a lot because it sounds like a really snappy name for a textbook title or something. Analytic geometry is basically, well, on the European side of things, for hundreds of years, variables and geometry were kind of two different tracks. And so when you saw a variable, it might be like Bob has X pigs and Jim has 6 pigs, and together they have 9 pigs or something like that. And it wasn't really until René Descartes came along. René Descartes was the first person to tie variables to each other. And from that, he was able to graph the relationship. And once he was able to graph the relationship, that really caused geometry and algebra to link up. What I really enjoy about these problems, and what kind of makes me hyperfixate on them, is that link. You kind of toggle between thinking about things geometrically and thinking about things mathematically. And the thing is, this is more upfront work, but when you really master this, it's a lot less work in the long run, because just plugging numbers into formulas is super boring, and you feel like you have to do it a long time before you memorize it. But if you're using those numbers as tools, or using those formulas as tools, you kind of remember them better. Because, I mean, if you think about it, the best way to really memorize what a screwdriver does is to knead it. And that's kind of how formulas work as well. So let's take a look at this, and let's see if we can do this problem. I'm pretty sure we can, because I already did. So let's have a look-see here. This is my second one here that I've prepared. There you are. And really, this is just a straight-up invocation of the Pythagorean theorem. So effectively, R1 is this whole distance. If I add that and that together, that's R1. I'm going to just kind of, I'll disable that temporarily. So here's the exact diagram we started with. And if I enable the rest of this, how I constructed that, again, R1 is the whole length, meaning that's R2, that's R2, and really it actually ends up being the case that the formula we're looking for is a result of applying the Pythagorean theorem to this triangle right here. If you use the Pythagorean theorem on that little sucker right there, a squared plus b squared equals c squared, everything just falls right where it should. It's actually pretty awesome. And that's, again, I'm not going to do the whole proof in front of you because I know not all of you are mathematicians and that would be boring, but really that ends up being the essence of this entire problem. So it's not nearly as difficult as it looks. And what's cool about it is that then you can take that further. You can nest more circles with other circles, and this formula will get you through really any dilemma that could arise as a result of that, which is kind of cool. Okay, back to my slideshow here. Oh my goodness. I have really got to figure out, oh, there we go. Let's take a look at another one. So this is a really interesting problem. So this one effectively says that we have two circles in our plane, so two circles being drawn, and they intersect somewhere. And I'll tell you right now, the points they intersect are super ugly. But what's cool is it's going to turn out we don't need to know specific points. And I'll show you why as we go here. But then we want to find an equation for a third circle that has those same two intersections as well as a third point. Now, if you were doing this in a trig class, the first thing you would probably do is make equations for both circles, set them equal to each other, and then work out the individual points. I did that. It took a really long time, and it was really tedious, and it turned out I really overthought it. There's actually a kind of obscure technique here that's super cool that makes this just a heck ton easier. And I didn't know this existed until I was reading a book in Japanese about this subject. So let's take a look at that. And this is a really wild problem, in my opinion. I know that I'm using the word wild very differently than most of you are, but it's my passion project, it's my day, suck it up. Okay, so what we have here, so here's the original diagram. I'm going to just get rid of some stuff here. And so we have these two circles. And as I was saying, Our goal really is to draw a third circle that goes through here, here, and there. Now, is that something you could do by hand?
Yep.
Yeah, absolutely. I think all of us could figure out how to do that by hand. Now, making that work mathematically, obviously another story. But I already did the work for you. As you kids and younger colleagues say, I got you, fam. So let's take a look at our equations here. So I made equations for these circles, and this is what's really cool. You can do what's called a linear combination, which means I can take the left-hand half of the blue one, I can take the left-hand half of the red one, and by adding and subtracting those repeatedly with strategy, I can actually make another circle that crosses them. So it turns out, if I just take my first circle part right here, and I just take my second circle part right here, and multiply that by a variable, then all I actually have to do here is find which value of k crosses that particular point. And I'm off to the races. That's actually the whole problem. So by using a linear combination, instead of trying to find every little thing here, by just adding and subtracting my equation strategically, I'm able to make a circle that's actually pretty painless. That's actually a heck ton easier than trying to find every little point and measuring everything out. It's also super satisfying. I mean, look at that. Look at that! It's so cool! All right. I know I'm going kind of fast here because I don't expect all of this to make sense the first time you see it. I'm just sharing a hyperfixation, and unless you've been hyperfixated, well, if you have, you understand. So yeah, onward. And again, let's see if this will start working. Awesome. So that's how we do that. Okay, we got the two tangent circles, we get the variable circle. Okay, this one I'm not going to show you the solution for, but I will tell you right now, this sucker took me a month. This one took me a really long time. I spent a long time scratching my head over it. I remember over the break, I was actually begging David Mayhew here for help, and he was just like, I'll get to it when I can. Yeah, he did what he always does. He was like, nobody cares, slop. That's totally how he talks. Yeah. I'm kidding, David was very helpful. But in any event, what this says is, it says we want to show that the incenter of this triangle is always the center of this circle. Now, an incenter is what you get when you take what's called perpendicular bisectors, or perpendiculars here, and if you perpendicularly bisect, you get the incenter. And what happens, the incenter is basically the point where a circle strikes inside of a triangle like that. And so effectively, this proof is to say the center of that circle always lies on that circle, no matter how you manipulate things. And this one took me a really, really long time. I don't think I prepared a solution to this one. I'll check. I didn't do a full solution, but I might have prepared a diagram to show you what's going on. Yes, I did. Awesome, right here. So here's the solution, or here's the diagram that I made. So you can kind of see here, basically, the incenter is where a whole bunch of perpendicular lines meet. That's what that is. And you can see here the center of this circle, the center of the little circle, always does indeed lie right on the big circle. Now again, this was a nightmare to prove. This took me a very long time. And this was a problem from, I think, 1821 or something like that. So, unfortunately, for a problem that old, I couldn't find a solution. You'd think someone would have written the solution down, but apparently they were just happy stumping me for 203 years. So yeah, you can see here that this is, yeah, it looks like no matter how I move this point around, no matter how I manipulate that point, indeed, it does look like the center of that circle is always on that circle. And that is indeed the case. It took me a very long time to prove why. Turned out I had to use some trigonometry here. Well, I don't know if I had to, but I kind of just gave up on everything else. And yeah, it ended up working, but it really did take a while. Okay, back to Jan's slideshow. If it decides to work, there we go. Okay, onward. So this is another one that's kind of related. So that previous one was a historical problem from 1821. This is a more modern problem on college entrance exams, which you can see has a lot of similarities. There's still a lot of circles, a lot of tangency, and this is a kind of problem that a high school student would probably want to be able to solve pretty quickly in about 20 minutes if they want to get into a good college. In this case, Mayville University. And by the way, on most of these entrance exams, students don't get to use calculators, so that adds a nice touch. Relationship here. And what it really says here is, okay, we got these two circles. It says M is that little line down there that strikes down there, and L is this line that goes that way. Sorry to anybody listening to the recording, I had an itch. Okay, I got it. So we have these tangents here, and so the trick, or the challenge here, is to find the length from A to B, so the length from that striking point A to the lower point B, and to find the point from C to D. And again, this one looks pretty ugly. Really, all we know is that the distance between O and O prime is 10. We also know that our radii are 5 and 2. This one also took me quite a while, but it was kind of cool. And again, it forced me to think about why things work the way they do. And so let's take a look at this sucker here. I believe I put that, yep, this is it right here. This one took me a long time to construct, actually. It took me longer to construct than to do. And so the trick to this one, and I should call this step 0 really. Okay. And so I constructed a bunch of things. What I did is, as you can see, I made a parallelogram. So I made a parallelogram that joined O and O prime. And by doing that, I was able to figure out some relationships. I was able to figure out that's 5 units long, that's 10 units long. And by doing that, I was able to really get the distance between A and B here. So that took care of that. I think I wrote it in the comments somewhere. Nope. And then, so that took care of that one. And then for step 2, I basically made a trapezoid here by using that parallel relationship. And so the trick in this case was, if you think about it, this and this have to be perpendicular. That and that have to be perpendicular. This and this also have to be perpendicular. So by constructing shapes around the shapes that I already had, I was able to use geometry that I was already familiar with to work all of this out. And I know I wrote the answer down somewhere. Not here apparently, but somewhere. I think I wrote it. So here's my variable circle problem that I showed you earlier. And so for those of you watching a recording, feverishly writing down every little step, here you go, you're welcome. There's the first part. And then here's the second part. You can see when I actually write it out. You'll notice that I always do my math in complete sentences, which is kind of a bigger time investment, obviously. It does take longer. But what I like about this is that a lot of starting math students will just not think about what they're doing. They'll just do the same thing over and over again. Then when they see an exception, they don't know how to handle it. They just think everything is arbitrary. Oh, this is true until it's not. That's true until it's not. You'll find if you take time to just consciously think about what you're doing, it's almost like a meditative sort of thing. It almost kind of feels like the solution is a wave on an ocean that's just making its way to your brain. I'm mixing the heck out of my metaphors, but don't think too hard about that part. Okay, so yeah, I did work this out, and so this problem I worked out by, again, for the first part, I made a parallelogram, as you see. And I did that by dimensioning parallelogram, and by doing that, and by using various and sundry theorems and things that have to be perpendicular, I was able to work out that the distance between A and B works out to be the square root of 51. Similarly, the distance between C and D works out to be the square root of 91. And again, I'm not going to drag through every little step because I know you'll find it boring. I would if it were me. But that's the process I did. I basically just constructed new shapes using what I knew. And again, the essence of problem solving is just really asking yourself, what do you know? And what do you know because of what you know? And how do you connect that to what you're looking for? And you'll be surprised at how often those blanks kind of fill themselves in. And it's a really exhilarating feeling. I know it doesn't feel like it if you're not a nerd, but it is one of those nerd things that is very affirming. So as I mentioned, René Descartes was really the first guy to come along and basically kind of combine geometry with algebra. He was the first person to come along and say, okay, we got this going on algebraically, we got this going on geometrically. Can we use these things to feed each other and solve problems that way? And so before that, people were just kind of lost in terms of how to solve a lot of problems. And one might say they put Descartes before the horse. Because his name is Descartes, you see, so. Okay, so a lot of problems, a lot of these entrance exam problems are about looking for high points or low points. They're about looking for, or Vicente, as you might agree, they're about looking for the difference between, say, 1 hot minute and Stadium Arcadium. And so in that case then, they're just not the chili peppers out of Frusciante. I said what I said. So next up, let's say we have, this is a very old problem. This is a historical problem from Koki. It's that 1600s book from 1621. And it basically, this one's interesting because it actually gets into calculus territory really quickly. You basically have a chunk of a cone, so basically a long tapered log, as it were, and you want to cut that into 3 logs that have the exact same volume. All you know about this tapered log is how tall it is and the circumference of the top and the bottom. This one gets ugly fast. I'm not even going to lie to you. This one gets ugly fast. But it's also kind of cool because it's hard in calculus sometimes to find problems that are really close or immediately understandable and how to translate that into something that calculus would be useful for. In calculus, we often find ourselves doing these weird problems where there's one classical calculus problem is you take a shape from taking a can of cranberry sauce and cutting it from 2 directions with the can itself. It's a really tricky thing that turns out to be a pain in the butt to integrate. But this is something where you can intuitively understand what you're looking for, but it actually turns into a pretty interesting calculus problem pretty quickly. I can't remember how I solved that, and I checked my work and I turned out to be wrong, so we'll just never speak of it again. Next problem. I like this problem. So this problem, this says, okay, we're going to take a parabola and we're going to trap it in such a way that basically we're going to take the whole parabola and put it inside a box. So we're going to put the whole parabola in a box where you know the top, bottom, left, and right hand sides. Okay, I prepared this one too. So I'll just mosey on out here. Let's see here. And I'm going to dig that sucker up. Yep, this one right here. Okay, so we have a parabola. We want to put it inside a box. I'm going to get rid of these future steps here and just take things one step at a time. And the mystery is, what are A and B to make this happen? So I can adjust A, I can adjust B, and again, here's what we know. We know that we want the maximum. We know we want this to strike the top right at 12. And if you think about it, the part of the parabola that has to strike the top has to be the vertex. Because if you think about it, this little tippity top part here, that's the part, if this hits its highest point, that's where it has to hit, right? Makes sense, right? That's what's called the vertex. You could also call it the Big Bend. Okay, it seems like you don't all understand. It's because it's the name of the school, you see it. All right, and then if you think about it, we want to hit one of these corners down here. And it turns out if we hit the right corner, then we're going to have stuff outside the box, and that's not good. So we want to basically, so the task here is to manipulate A and B until our parabola hits that vertex up there and that little corner point down there. And eventually, if you do this, you get 2 simultaneous equations, negative A plus B equals 12, and 8A plus B equals 6. And I'm just going to fix something here real quick. I just like that little italic text right there, so I'm just fixing that right now. Beautiful. And so then it turns out that this works when B equals A plus 12. So what I'll do is I'll set B to be A plus 12. Now, what I can do is just move this until it just slides right into place at 10. And there you go. And that is how you do it. So now we're able to put this whole parabola inside a box where there's nothing directly above or below it, which is what we wanted. And that's how it works. And so you can see here a problem like this forces us to kind of, again, toggle between algebra and geometry. What has to be true if the maximum's 12? What has to be true is that the Big Bend has to strike the top of the rectangle at 12. And in this case, we're figuring out what's further away from the vertex. Well, the left-hand side has to be further away, so we're going to shrink that to fit in place. And so just by thinking about the geometry a bit, we're able to take this ugly, ugly problem and actually make it surprisingly simple. Okay. Next up, this next one, if it's the one I think it is, this one is a fun one too, in my opinion. Here we are. Yes, this one is amazing. Okay. So, again, I need to remind you, students taking entrance exams don't have a calculator. So if you want to get to Sophia University, at least in this particular year that when this exam took place, what you need to do is be able to multiply 100.1, take that to the 7th power. Now, you could do that by hand, in theory, but you all lead fast-paced lives in the mean streets of Moses Lake. You don't have time to write 100.1 times 100.1 times 100.1 7 total times. That's ridiculous. It turns out There exists a better way. And it turns out it actually has links to, of all things, scientific notation. By using scientific notation to your advantage, and also something called Pascal's triangle you've probably heard about. And so it turns out by using those things together, you can actually do this by hand, and it's not nearly as hard as you would think. Let's take a look at this right here. So here's Pascal's triangle, for those of you who've never seen it. I'll zoom in a bit here. So Pascal's triangle is basically a giant stack of hexagons, and the way that it works is that each successive number is the sum of the two above it. So 4 plus 1 is 5, 10 plus 5 is 15, and so on and so forth. The very tippy top is the 0th row, then the 1st row, then the 2nd row, all the way on down. And we're going to use the 7th row right here. So the numbers we're going to use are 1, 7, 21, 35, 35, 21, 7, 1. Memorize those real quick. Think of those right now. So 1, 7, 21, 35, 35, 21, 7, 1. You only really need to memorize 4 numbers, but burn this in your brain like those 6 numbers from Lost, because we're going to use them very soon. Now, I'm going to go to this part right here. Oh, wait, hang on, wrong thing. There we go. So I'm going to just get rid of some stuff here. And so the thing is that we can construct this thing, and I prepared something here. I like this problem. This one's very satisfying. And again, here's the 3 frustrative problem. I'm going to scroll quickly because I'm pretty sure my answer's wrong. And here is the parabola and range problem. And yeah, here we go. Okay, so what I did is, if you think about it, this is the sum. This is 100 plus 0.1. We have a thing that some other colleges teach in pre-calculus called the binomial theorem that basically says that we can expand something and its coefficients, basically if you take a binomial to a power, the coefficients turn out to come straight from Pascal's triangle. Now, this kind of looks pretty dry as it is, but let me show you something. So what I did is I laid out all my places here. I laid out all the places. And it turns out here, if we take our place values, basically they're those same numbers right there. 1, 7, 21, 35, 35, 21, 7, 1. It works out that by basically applying some strategy in terms of how we expand our binomial, this is the placement of those same numbers, then the 0 place values go here, and I literally did that without a calculator. Without a calculator, I was able to figure out 100.1 to the 7th power by just using scientific notation to figure out where along the number each of our little numbers go, and by doing that, we're able to construct a bigger number. It's actually pretty cool. You might not think so, but I don't care. So onward. All right, so onward. This is another one that my 141 students hate. So with this one, what we do is, again, this is another example of geometry and algebra coexisting with each other. So we're going to take a parabola, and we're going to rotate that parabola. In fact, because I've just been kind of droning at you, let's do an activity. Y'all have pieces of paper here, right? I'm going to do an activity. I already do this in my Math 141 class, so if you're in Math 141, pretend you don't know where I'm going with this. All right. And could someone give me a piece of paper too, please? Because it's easier if I show you. Okay. We're going to do a little activity here. I'm going to teach you how to make a shape with origami that turns out to be relevant here. Now, take a writing utensil and take a piece of paper, and I want you to take your writing utensil, preferably a marker or a pen, which a lot of you seem to have, and I would like you to just run your writing utensil along one edge of the paper. Just really get one edge of the paper, really just get that good and neat. Okay, so run along one edge of the paper. Okay, step 2. Somewhere in the interior of the paper, draw yourself a point. Doesn't really matter where. Try to get it somewhere in the middle, though. It'll make things a bit easier. So I've drawn myself a point. Don't worry, this isn't the whole activity. So I have basically drawn a line, and I've drawn a point. Is this making sense so far? Draw a line, draw a point. Okay, it gets harder from here, so I want to make sure we're good. Ready for me to move on? Okay, the next step's a doozy. All right, here's what we do. I want you to fold your piece of paper. The angle doesn't matter, but I want you to make a crease in such a way, and again, the angle doesn't matter here, but make a crease that causes the line to cross the point, just like I did here. So I folded this, my fold is crooked, that's kind of what it's supposed to happen, so that's okay. But fold your piece of paper in such a way that the line is going right through that point. Okay. Awesome, looks like we're on the same page here. Now, I want you to do that again. Make a different fold, but again, make the line cross the point. So different fold, I'm folding this right now, and make the line cross the point, just like I did there. Now, I want you to just keep doing this. Make as many folds as you possibly can. Just make a whole heck ton of folds here. As many folds as you can that cause the point and the line to cross. And the more perspicacious among you will eventually see a pattern form. But basically make as many of these as you possibly can. You'll have to kind of be a bit mean to your paper, but that's okay. Think of the paper the way I think of my junior colleagues. Oh, that reminds me, a couple of you are on some new committees, so talk to me after the talk. So, yeah, just keep doing this as many times as it takes. Now, what happens here is you will eventually get a parabola. See, here is what I just had to do, and here's why I had to do it. So what I'm doing is I'm just tracing all those folds that I just made. And if you do that, that is a parabola. So here's the thing about parabolas. Parabolas are basically a figure that is the most efficient reflector in all of nature. Because every point on a parabola is such that the distance there is the same as the distance there. This point is called a focus, this line is called a directrix, and when you're folding, you're basically finding a symmetry between them and making what's called a tangent line. And if you make enough of these, you can fold yourself a pretty good parabola. Another way you could see a parabola if you wanted to, and I think I might have saved this to the wrong spot, so I could be wrong here. But let's give it a shot. I think I made this previously, so I'll double check here. If not, it's not that hard to remake, but I will show you. Cruddy crud crud. I don't think I saved it. Dang it. That's okay, I'll show you anyway. So let's take a look. So let's say we have a focus, I'll call it H comma K. And we have a point that's floating around in space, just free floating, like my hostility. And I'm going to make a point P, or I'll make a value P called 1. And what I'm going to do, this point right here is going to be the vertex. And what I'm going to do is take H comma K plus P, like that. And this point is going to turn out to be my focus. So I'm putting a focus right there. The directrix will be at Y equals K minus P. And what I'm going to do is make a whole ton of lines. But first, I'm going to get the colors how I like them. So all I'm doing right now is just making the colors nice and pretty, just because I like the way it looks when I do. So I'll make the focus red, I'll make the vertex purple. Okay, another way you can draw a parabola. I'm going to teach you another geometric sort of method for discovering a parabola. What I'm going to do is make a whole bunch of integers. So I'll say n goes from, say, 1 all the way to 20, I guess. And what I'm also going to do is just draw some horizontal lines here. So I'm going to put y equals k minus p plus n. Okay, so I made a whole bunch of parallel lines here, just like that. And you can see they're all parallel, just like I have here. Okay. And then what I'm also going to do is I'm going to make a whole bunch of concentric circles. So I'm going to do this. Obviously you don't need to know what all I'm doing here, but I'm going to make a whole bunch of circles that all go around the focus. There we go, gorgeous. And so I made a whole bunch of concentric circles. I'm going to reduce the opacity because even I'm looking at this and thinking that's kind of a lot. So let's make these a little bit more transparent so you can see where I'm going with this. All right, well as I said, a parabola is defined as basically every point that is equidistant from the focus and the directrix. And that means that you can actually draw yourself a parabola by just tracing all of these points. So what I will do is draw y equals 1 over 4p, I believe it is. I could be wrong, I'm going from memory. And then I'm going to have here x minus h squared plus k. And what I want to draw your attention to here, if you look closely, is, and again, I'll move P down so you can get a better look at this, but what I want to draw your attention to is that every single point on this parabola, if I had done this right, which apparently I didn't, so what the heck went wrong? Let's see here. Maybe negative? No, I guess it would be positive.
Yeah, you're good.
I'm good?
Yeah.
Okay. Oh, I know what's going on. It's because they're not integers. That would do it. They don't have to be integers. It just is easier to see if they are. There we go. And so it turns out here that basically you can make a parabola by just crossing intersections where the focus and the vertex touch. That's actually all a parabola actually is. So if I put that, say, right there, you can see that point strikes there and there. You can see that we have another point that strikes there and there. And so by, oh, it has to be around the focus. That's what it is. I apologize. So this is actually y minus k minus p. There we go. That looks a lot better. There we go. And so if you look here carefully, I'm going to make this a little bit thicker. I'll paint it blue. Let's make that double thick right there. And what I want to draw your attention to is that the symmetry here, notice that blue line is hitting intersections between the circles and the lines here. So basically, this point right here is 2 from the focus, 2 from the directrix. That point is 1, 2, 3 from the focus, 1, 2, 3 from the directrix. 1, 2, 3, 4 from the directrix, 1, 2, 3, 4 from the focus. And you can actually draw a parabola just as all of these intersections. And that's another geometric construction of a parabola, which again works the exact same way. It consists of basically points that are the same distance from a focus and a directrix. Oh, come on, that's so cool. Look at that. Are you not entertained? Thank you. And so now let's talk about moving this parabola right here. So if I take a parabola and I move it, so the first thing I'm going to do is rotate it by 180 degrees about the origin. Then the next thing I'm going to do is rotate it 3 units rightward, 6 units upward, and I know what I get when I land. And so now, again, I have a challenge of uniting the geometry and the algebra. I got to say to myself, okay, well, how am I going to flip this sucker? Then how am I going to move it? And how do I get it where I want it to be? And so to do that, I shall show you because I am so nice. Let's take a look here. So this is that problem. So the trick here is to kind of use the vertex as a handle. So the purple is the parabola we want. The red is the parabola we have. And I really just want to adjust A and B until I get where I want to go. And again, what we can do is use the vertex as a sort of handle. So if I take my vertex, I'll move this so you can see it better. So basically what we can do is I can take the vertex and rotate it by 180 degrees. In algebra, that turns out to be the equivalent of taking the negative of x and the negative of y. So I made myself a function where I just took the negative of x and the negative of y. That's all I did there. Then I took that function. Now I'm done with that. Or not that yet, just yet, but I'm done with the red. And now that I've moved that, now I'm going to move that little thing 3 units rightward. So I did that. Then I'm going to move it 6 units upward. And now that I've done all of those things, now I want the blue to match the purple. And you can do all this algebraically. It works out, I believe B is 10 and A is -2, it looks like. Yeah, look at that. Fits like a glove. And so, yeah, this is a case where if you just use the vertex as a handle and imagine yourself moving the vertex, everything else follows suit, which is kind of spiffy. All right, obviously I'm not going to have time to do everything I have planned for you, so I just want to show you some of the cooler things. First off, I'm going to show you this one primarily because there are a bunch of cranes in the background, so this is my way of thanking you for folding all them cranes. And so, circle obtained by folding, this one looks really difficult. Like, you can look at that one, and that looks like a whole lot of work. And it kind of is. But the cool thing about it is, again, if you think about it geometrically, it's actually a paper tiger. It looks really difficult, but it's actually not bad at all. I shall show you. So, that's the one that I have. Let's see here. I don't think it's that one. No, it's not that one. I don't think it's that one. Oh, it's this one, actually. Okay, here we go. So what I did is, first off, I constructed my semicircle, as you see, and I basically made a chord on this semicircle, which is right here, and then I reflected the circle there. Now think about this. What I've done is I've reflected a little bit of arc around this line. Now, if you think about it, that probably looks really complicated. Wouldn't that arc have to have the same radius as this arc? They would have to have the same radius, right?
Yeah.
If you think about it, yeah. And so, based on that common radius, now if you think about it, the other thing they specify is that this length is identical to that length. What are you noticing about these two green lines? What stands out to you?
Perpendicular.
They're perpendicular. They have to be in order for this to be a circular construction. And based on combining those facts, we can actually get the center of that arc pretty quickly. And based on the center of that arc, I can now again make another circle that hits that point using that little trick I told you earlier about the linear combinations. And that gets me my circle, and that gets me the point that I need. And now the other part of the problem is they're asking us, how do I move this so it's as big as possible? Well, if you think about that too, that would have to be like this. If that point's as big as possible, then it's got to cross both centers. And that's actually it. So again, I know I'm very much glossing over this, but the point that I'm trying to make here is that by looking at the geometry and thinking about it a little, you can do a lot more than you might think you can. And then I wanted to show you, I'll show you 2 or 3 more problems. I'm going to try to wrap it up here because I'm such a nice person. But I wanted to show you a problem that David here and I spent a long time on. Is the tangent of 1 degree a rational number. This is from Kyoto University, which is probably the second hardest school to get into in Japan. And so the trick here, this is figuring out if the tangent of 1 degree is a rational number. And David here and I both did this problem independently. And what we did is we basically chained together a bunch of trig rules to get up all the way up to the tangent of 30 degrees, which we knew for a fact was an irrational number. What I often do when I'm doing more difficult problems, I'll tell you honestly, I will make a personal confession about myself. I have ADHD. That's actually true. It's diagnosed. I take pills. They're legal. So I have ADHD. And so I have difficulty with executive functioning. And so sometimes when I do a proof, or when I do an ugly problem, I lose my way too. And I say that because I don't want you to feel bad about that. Even when I do math, I get lost sometimes too. Even I don't always know what I'm doing, and that's okay. So sometimes I like to make my work in the form of a flow chart. This is the flow chart I made here, and I know it's kind of ugly, but I did that because I wanted to show you that basically, by organizing my own work, I was able to figure out where everything goes, and I was able to find that the answer here was no. And I did that by getting to this point. This says, I know you can't see it, but it says no number can be both rational and irrational. So what I did is I chained together a bunch of logic to get a rational number and an irrational number for the same number. When that happens, the universe explodes, and that would be bad. And so I used that to conclude, okay, if that would be bad, then it can't be true, and that's kind of the basis of logic. So I said Kyoto University is the second hardest school to get into in Japan. The hardest is Tokyo University. Here's an actual entrance exam problem from Tokyo University. Prove that pi is greater than 3.05. Now, one thing you will learn, and I'm sure most of our mathematicians, most of my colleagues would agree with this, the really scary problems are the short ones. When a problem has only 1 or 2 sentences, you're in a lot of trouble. And this is actually a pretty difficult problem. Again, it looks really quick, and I know what you're thinking, just use a calculator. Oh, wait, nope, you can't. That's right. Yeah, no calculators for you. And so you could, in theory, represent pi as a sum, which you learn how to do in calculus and add up a whole bunch of numbers, but that's extremely tedious, and there's a better way, again, using geometry. So, let me show you something I taught our trig students this quarter, and that is, I'm going to take a look at a proof that pi is greater than 3. We'll start with just 3. And it's actually not that hard to prove that pi is greater than 3. The trick is, we take a circle, and we put a hexagon inside it. And so I have a hexagon inside a circle. I'm actually going to make one slight modification here because it makes some stuff more obvious. Instead of making the radius 1, I'll make the diameter 1, so I'll make the radius 0.5. Now here's what's happening. If I count all the way around the circle, or if I count all the way around the hexagon, if I find the perimeter of the hexagon, well, that length is 0.5. Last I checked, hexagons have 6 sides. So what's the perimeter of the hexagon? 3, right. The circumference of the circle, well, the diameter is 1, the circumference is pi times that, so this is actually a proof that pi is greater than 3. The idea is we know that the circle is bigger, because that's in plain sight. You can tell by looking, it takes longer to go around the circle than it does to go around the hexagon. The circumference we know to be pi, so we've already proven that pi is greater than 3, which is great, but still not getting into Tokyo University. And we really want to get into Tokyo University because that's where like the politicians and the bigwigs go, and that's great for hobnobbing. And I know what all of you in your 30s and 40s are thinking, and maybe it's not too late. I'm kidding, it's totally too late. So what I'm going to do is increase the number of sides here. Let's say we're looking at a heptagon instead. Okay, that's a little bit bigger. Oh, once I get to an octagon, look at that, then the length does exceed it. And so it turns out the trick here, which you can absolutely do by hand if you're really good at trig. If you're really good at trig, you can say to yourself, okay, that's a 45-degree angle. I could use that to get that side, make 8 of those, and that does indeed work out to be more than 3.05. It's a little bit of work, but it's well within your power if you've mastered trigonometry. And you can totally do that with a calculator. I know because I did. In fact, I think I have my work for that somewhere around here. And I'll show you later. So I wanted to show you, I'll close here with a couple more problems. So one famous problem is called the Josephus problem, which is basically eeny, meeny, miny, moe. And that is, so it says here, a man has 30 children, 15 by his first wife and 15 by his current wife, like you do. And he decides to choose one child to create or to give the inheritance, also like you do. There was a documentary about this called Slasher Season 4. And thank you, audience person who's definitely not my girlfriend. And so what we're going to do is choose one child to receive the inheritance, and what we do is we just count all the way around. And we count all the way around, randomly eliminate one kid at a time until one kid remains. And this is actually a pretty interesting problem. This is another historical problem. It's about 400 years old. And I wanted to show you, the last problem I'm going to show you is the one that's the reason my Calc 1 students hated my guts. I thought it would be a good idea to give my students extra credit after the first test. And the extra credit I gave them, they hadn't seen maxima or minima yet, and I would be willing to admit this wasn't the smartest thing I ever did. It seemed like a good idea at the time, I wouldn't do it now. So those of you who need to retake Calc 1, I won't give this next quarter, so don't worry about that. But basically find the highest and lowest points of that whole function right there. Now, this function, as you can tell, is pretty ugly. My students were pretty pissed off that I gave them this. There's actually a trick to it though, and I'll show you what the trick is. The trick is noticing that we actually have the same expression twice. That is all one expression, that is all one expression, and also they're both non-negative, which is kind of nice. And so then, again, I made a flow chart of my work here. So here's how I flow charted this sucker out. I know you can't really get a good look at it, but basically what I did is I took my function, I found the maximum of the little inner function, and I basically weeded out false solutions or situations that had no solution, and I arrived at a minimum at 0 and maxima at the endpoint. So this one actually isn't that bad, you just kind of have to think at a very, very high level. So I've done hundreds of these problems, but I really wanted to kind of cap things off here by talking about what these problems taught me and what I've learned from doing them. Because I feel like doing all these problems has made me a lot better at thinking. Not necessarily just in Japanese and math, but just thinking in general. And so really I learned 3 things. Stop, collaborate, and listen. And that's what good mathematicians, ask your parents, it's what good mathematicians do. So really you can do a lot by just stopping and thinking. So the first thing you do is stop, write out your thought process, describe the goal as precisely as you can, because you'll often discover you need less information than you think. If you need a third circle that crosses 2 other circles, you don't need every little detail, you just need something that'll work. And so you often need less information than you might think. And also, in a lot of ways, to collaborate, I often think of math as a Metroidvania game, or as being a detective, or even as being a lawyer. Because past problems you've used are like case law, and you can use those on future problems. And in a lot of ways, what you're doing when you're proving theorems is you're making an argument, and you're saying, ladies and gentlemen of the jury, here's why pi has to be greater than 3.05. And by putting these things together, you're able to make an argument that really no one can say no to. And while proofs do seem like a lot of work, a colleague of mine, or someone who I think is a better mathematician than me, refers to proofs as the lifeblood of math. Because again, proving a theorem is a lot like getting an item in a Zelda game. Once you know something is true, nobody can take that away from you. If you brain fart, forget a formula on a test. If you know how to make that formula, you never need to remember it because you just know how to construct it. Just like in real life, if you know how to build a fire, then you're pretty well prepared for when an inch of rain falls in Moses Lake, at least if you live in the base, like I do. And then finally, just knowing how to use theorems properly, considering where things go, when things work. Because really, a lot of things we think are exceptions aren't really exceptions. We often think in math that this is true until it's not true, or this works until it doesn't work. And that's not really the case. What's really the case is just that if you sit down and think about what's going on geometrically, it's actually often pretty obvious. Anyway, my last slide here. I didn't get to where I was without a lot of people helping me, including Lindsay, actually, who is one of my best friends in the world, which is why I asked her to introduce me. And I wanted to close this out with a shout out. About 4 years ago, my first mentor, Mike Kenyon, passed away, and yeah, he meant a lot to me, and I think he's the reason I'm doing this. And I just wanted to say that this is for him in a lot of ways, because I feel like I owe him everything I became. So, yeah, that's all I got. Last thing, Washington is a two-party consent state, so by being in this room, you consent to being recorded. All right, thank you all. Any questions or anything?
I do have a question.
Yeah, go for it.
So, about procrastination in advice.
Yeah, actually, what I tell myself a lot, because I am a terrible procrastinator, and that's why none of you know where I live, because if you looked at my yard, you would not think I was qualified to give advice. But I would say what always helps me, and what I tell my students a lot, is that not enough is still more than zero. So like one thing I have to do, I have this table that I need to clean off, as my girlfriend knows. And so I often tell myself, okay, I might not get this whole thing cleaned off, but if I move this one piece of paper, if I throw away this little piece of mail or something like that, even if I'm not doing very much, I can still at least tell myself, hey, that's still more than if I did nothing. Or sometimes might go a couple days without studying Japanese. And of course, my first instinct, as I'm sure is the case with a lot of you, is to beat myself up. I'm like, oh crap, my Japanese sucks. 30 years of this just went down the drain. Oh no, the world is ending. Dogs and cats will be the mass hysteria. But then I just have to remind myself that setbacks are a part of life. And if I just pick up my phone, I have an app called Anki on my phone. And so what I do every day is I fire up Anki when nobody's looking or when I'm at a boring meeting. And then what I will do is it gives me a list of flashcards, and I'll just knock out a few of those. Right now, this is the kanji for island, I believe. Nope, it's ivy. Okay, got that wrong. But I'm okay with being wrong. Okay, this one is haku, which means oak. Hey, got it right. So I just did 2 cards. Now, that's not a huge amount, but that's still more than if I did 0. So I sleep a lot better knowing I did something. I made some progress. And also as a side benefit, if your parents or your friends are like, well, did you just start tonight? You'd be like, no, I didn't just start tonight. Maybe you didn't do much, but that's still more than you did nothing. So yeah, what I always tell myself is not enough is still more than 0.
Yeah. All right.
I wasn't looking for class. Other questions? Questions, comments, clarifications? Anything stuck in your craw? Anything you need closure on? Yes, sir. Vicente.
The bamboo problem, where
Yeah.
changing size. Do we have the equations for bamboo? Is that necessarily solving?
I don't think you need the equation. I think you need the dimensions, because from the dimensions you can make the equation. Yeah, because all you need to do is make a line that connects them. That's a really good approach, actually. I like that. I might try that. Other questions? All right, so I did make, so I will show you something. I don't know how to show you this without going into my personal Google account, and frankly, it's none of y'all's business. I don't need your I don't need your judgmental looks, but I've been working for about over a year now on a collection of Japanese entrance exam problems. So I've translated about 125 of these so far. I've gone through all of these. I've translated them. I have translated the original problem, I've solved it, checked it against the solution in Japanese, and I've actually coded about 50 of these into WAMAP as practice problems for my students, including this one that turns out to be where a cycloid comes from. And so if any of you would like a link to this, just let me know at some time that isn't right now. I have it on Google somewhere and I can get you a link. So if you're ever interested in doing lots of difficult math and checking your work against how I did it, just let me know. All right. That's all I got. Thank you all.